Okay, so what we're going to do in the Excel portion of this is still B, this is A, and that's C. All right, what we're going to do is follow the same process that's up on the whiteboard, so that along the way we're going to compare the numbers that we get in the spreadsheet to kind of what we've done by hand as a reality check to make sure that there wasn't any calculation errors and formula mistakes. But we'll know we're done when two criteria have been met. One is that continuity is honored, that the flow into the junction and the flow out of the junction is the same. And the other is that the F values aren't changing very much. So once the friction factor, because we're calculating it twice within each iteration, once it's stabilized and isn't changing within about 2%, then we'll say that's close enough.
So BD is our AD for now, right?
What?
BD is our AD.
BD is our AD?
Yeah,
No, on the template it's the same as that.
Oh, it is?
Yeah.
Okay.
Yeah. So just so that next semester they don't have the same confusion, I should call this one B, right? So would this eliminate all future uncertainty?
Yeah. Okay.
But then I'm going to have this called B and this one called A. I think now I've atoned for my confusion-inducing mistake. All right. So here we go. We're going to do this one using the template file that I provided. Here's the unknown. So we've got the Darcy-Weisbach equation. If we rearrange it, we can solve for velocity. We're going to be using the Jane equation to solve for F value. It's valid over the range of 5,000 to 10 to the 8th. So we'll double check our Reynolds numbers to make sure that we're in that range. And then you've got to remember we've got different material types there. So for our first iteration, let's start putting in known information about the system. We know that the K sub S value for cast iron, for example, is 0.00085. Okay, and that pipe BD is also cast iron, so 0.00085. Galvanized iron, though, has a different relative roughness, 0.0005 feet. Okay, we need to put in the pipe lengths. So pipe AD has 750 feet. Pipe BD is 1,000 feet. And pipe DC is only 500 feet. The diameter needs to be in terms of feet, and we've got it in terms of inches. So pipe AD is 8 divided by 12, and that'll give us the diameter in feet. Pipe BD is 12 inches, and so that's 1 foot. And then finally, pipe DC is 8 inches, so 8 divided by 12. Okay, and now we can calculate the area for those given diameters. So it's pi times the diameter squared divided by 4. I'm going to zoom in a little bit, although it doesn't give us the same bird's eye view of everything. It'll make this a little bit bigger at least. All right. So we can drag that down and it will apply the cross-sectional area formula. So is everybody with me so far on these physical properties of the pipes? Okay, so let's use the same guess as before. Let's say 110 feet. Even though on the board we saw that that guess is too high, let's prove it to ourselves again. And so we want the guess of H sub D is going to be the same for all of these different rows. And so I'm just going to have my cell reference go up to where I said 110 rather than typing it in again. Those will all just be referencing whatever value is here. Okay, here's not the hard part, but here's something where we got to kind of think for a moment. How much head loss is there through the pipe? So pipe BD is going from 120 down to 110. And so the head loss is going to be 120 minus this guess value. So there's 10 feet of head. Okay, pipe AD. Oh, hold on a minute. AD, oh, that's going to be 0 because it's 110 minus that, 110, so it's 0. There's no head loss through this pipe AD because the head at D is the same as the elevation of the water at A. It is pipe BD where now it's going to be 120 minus 110. So it's 120 minus 110. And then the head loss through DC is the head at D minus the head at C. So it's the head at D minus the head at C, which is 70. So I'm typing that in manually. Okay, now these formulas are different. For pipe BD, it's 120 minus. For pipe DC, it's the guess value minus the known elevation. And we talked about, where that comes from. It's the plus versus the minus back on this slide, minus or plus. Okay. So now our guess value of F, 0.02 for our first round of iteration. And if we have a guess F value, then we can use this to estimate what the velocity through the pipe is. We rearrange the Darcy-Weisbach equation, so let's do that. It is equals the square root of h sub f times the diameter times 2 times g divided by the f value. Now having the cells centered means I can't click on that location, because the formula is going into the space where I'd like to click. So I'm going to type in I-27 because that's the f value. And then I'm also going to divide by the pipe length. Okay. So there's no velocity through that pipe because there's no head loss. But if I drag this formula down, it's going to calculate those velocities. And if we check, remember it was 5.67 for BD, 13.11 for DC. Well, 13.10 is awfully close. So far, everything's shaking out as we'd expect. Did everybody get this step? Let me pause for just a moment and... Okay, so we've got a guess value of F, we've got the velocity that comes out of that, and so we can estimate the Reynolds number based on that velocity. So Reynolds number, I guess I don't have the formula on the handout on the screen there, but it's the velocity times diameter divided by kinematic velocity. So velocity times diameter divided by kinematic viscosity. And kinematic viscosity is 1.138 times 10 to the minus fifth. So in Excel, you can just put E minus 5 and it knows what to do with that. Okay, so that Reynolds number is 0 because the velocity is 0. But those are the Reynolds numbers that are pretty close to what we got before when we were doing all this by hand. And since now we have updated estimates of the Reynolds number, now we can go to the Jane equation and calculate F values based on that. So let me get that nice and close here because we're going to type in the formula. Okay, so the Jane equation, well, it's not going to be defined for this pipe. So I'm just going to say our guess value for this pipe remains 0.02. Because we don't have any Reynolds number, we're not going to be able to improve the guess of AD. But for these other ones, since we do have Reynolds numbers, we can improve the guess of the F value. So that's 1.325 divided by, parentheses, a logarithm of K sub S. So here's the K sub S reference. divided by 3.7 divided by the diameter plus 5.74 divided by the Reynolds number, and now the formula is in the way, so I'll have to type it in rather than being able to click. It's K28, gives me the Reynolds number, to the power of 0.9, and I close the parentheses for the logarithm, close the parentheses for the denominator, and square it. With any luck, it'll give me a value that's somewhere close to 0.02, but not too far away. Okay, 0.0215 is the updated F value. Oh, that's not right. Oh, yeah, it's because it's wrong row. Let me drag that down. That's more like it. Okay. Yes. And then I can just drag the formula down, and then it'll apply these, again, wrong spot. It's so strange. Why is it? Okay, now that's right. Yeah, correct row. Okay.
I heard the same thing on the first one, not the second one.
Well, I'm pretty confident that 0.0189 is right.
Yeah, that's why I got it.
Let's see. Rather than using the shortcut that I sometimes do, let me type in the Jane equation another way, just because I know that you can never type the Jane equation too many times. Okay, 1.325 divided by the logarithm of k sub s divided by, now I'm going to use the parentheses this time just to prove that it's the same, 3.7 times d, okay, close parentheses, and now I'm plus 5.74 divided by the Reynolds number, K29 to the power of 0.9, close parentheses, oh, wrong, there we go, and square it. Okay, so I still get the 0.0189 that I had when I just dragged this same formula. All right. So now we get a new guess velocity. So we're using the Darcy-Weisbach equation again for that improved guess of velocity. So it's the square root of h sub f times diameter times 2 times g, 32.2, divided by the new guess f value, so that's L27, divided by the length. Or if you want to put parentheses between it, then, you know, it's divided by f times L. Okay, so close parentheses. So we've got a new velocity, that's 0 because the Reynolds number and everything else was still 0. But you notice the velocities are slightly updated. And now let's calculate flow rates from that. And I guess we should pay attention to the direction. So in pipe BD, the flow is in, and pipe DC, the flow is out. So the water is coming, if we zoom out a little bit here, for pipe BD, the water's coming into the junction through that pipe. It's going out of the junction through pipe DC. So here's pipe DC, out. Okay, so the flow rate is just Q equals V times A. So we're using the continuity equation there, using the most recent updated value of the velocity, not that initial version. Okay, so we can drag that down, And then here, to check our error, we want to have out minus in. And we want that out minus in to be as close to 0 as possible. So what is the conclusion? If we go back to here to our criteria, if out is bigger than in, then lower the guess of h sub d. Okay, so our conclusion here is out is bigger than in. Guess of h sub d is too high. Need to lower our guess of h sub d for the next iteration. Yeah.
Could you, like the 0.210 there, could you do goal seek, set that to 0, and then by changing that first column of h sub d?
I like the way you think. He's asked an excellent question. He said, well, if our objective is for that difference to be 0, can't we just play around with our guess value of h sub d? We will get to that point eventually, but we can't yet because our values of f haven't got where we need them to be. And so this is like a two-factor convergence that we're looking to achieve. And so we can do that, but not yet. Are there other questions? Okay, so here's where things get nice. The reason why we enjoy using Excel, because we can just copy all this physical data, Control C, and then Control V to paste it. Don't have to calculate any of that again. So we need our guess to be lower. Let's just, for sake of consistency, I'll use the same guess, 109.5 as our new updated value. Okay, now we're going to have to think again. It's not all fully automated. We're going to have to reflect on what that means. If this is the head value, then how much head loss is there? So through pipe AD, it's going to be, the head loss will be 110 minus this value. So there will be half a foot of head loss through that pipe. Through pipe BD, it's going to be 120 minus this guess value. And then for the last one, it's going to be this guess value minus 70 feet. The head loss guess always needs to be positive. Okay, so our guess value of F, we have to just use this 0.02 for pipe AD because we haven't really figured anything out for that pipe yet. But for these other ones, we'll use the most recent version of the F value. So we use the 0.0197 and this 0.0189. And so now we can calculate the velocities. Just highlight that cell, Control C, paste it with the Control V, and it applies the formula, but with all the new data. It's using this F value. It's using this guess of h sub d. So we've got those velocities, and so we didn't have to type in the Darcy-Weisbach equation again. Likewise, we don't have to type in the Reynolds number equation again, because we can copy it from above, and we can paste it down into the next iteration. And the same thing is true of the Jane equation. We can copy, now we don't want to copy that one. Let's copy the lower two, Control C, Control V, and then we can drag it from this one up, and it will apply the Jane equation for that row. And finally, we've got the Darcy-Weisbach equation again, so we Control C, we paste it. Okay, now flow into junction. This is where we have to think again if it's flow in or if it's flow out. So pipe AD. The water is going, if it's 110 there and 109.5, that means the water is going from A towards D. So that means it is flow into junction. And this pipe BD is also flow into junction, but DC is out. Okay, the flow rates are going to be same as they were before, where we can copy the continuity equation down there and then drag it one cell up to pick up pipe AD. And now out minus in. Let's see the magnitude of our error. It's going to be this one out minus the two ins. And the error actually is worse than it was before. We overshot. Because before, the magnitude of our error was 0.21 cubic feet per second. So our guess is further away. And what it means is that there's more in than out. So let's write that in is greater than out. So should we raise or lower our guess for iteration 3?
Raise it.
We need to raise our guess for this h sub d value. So here for iteration 3, what I'm going to do is let's copy everything all at once. Just highlight all of these and Control C, and then paste the whole thing all at once. All right, and what we're going to change is this guess value of h sub d. And so we know that if we go 109.6, and we're going to check this and see if it gets closer to 0, which is where we want it. So 109.6, everything updates, and yes, it gets closer to 0. 109.7, it gets closer. The suspense is killing me. 109.8. All right. Well, it's been fun doing that manually, but let's automate the iteration. There is one thing that we can improve. You know how we did that whole bulk copy and paste? This value of f was originally keyed in as 0.02, but we have an improved guess there. So let's switch that to the improved guess of f from iteration 2. And that gets us even closer. Okay, let me pause for a moment. And okay, so here's where we're at. We were manually keying this in just to see if we could get closer and closer to 0. But we know that there is the, under data, what if analysis. So you can use goal seek, but I think goal seek won't work. Let's try. Does it? It depends, I think, on what convergence criteria it's got. So we want this to be equal to 0 by changing this value. And we turn it loose, and it rolls and rolls. All right. So that's pretty close to our final answer that we're going to get. By the way, what's the other tool that's similar to GoalSeek? Do you remember the name of that? Solver. Solver is more sophisticated. And when I was doing this earlier today on my own computer, I had previously set Solver that I wanted the answer to be really, really precise, and it was too precise. Like it wouldn't calculate the answer. It couldn't. It could never find a solution that was accurate enough, and so it kept failing. So I had to change the precision. And I guess down here on this machine, the precision was already set so that it would converge. Okay, so but remember, it's not just continuity that tells us when we're done. We want it to. We know we're done when n equals out, and also when the f values have converged within 2%. And so let's look at that. Let's check here the f values. And so I'm going to call this f change percent. Okay, so it is going to be the initial f minus this secondary guess of f divided by the secondary guess of f times 100. So the difference divided by the value multiplied by 100. Okay.
Thought about which f did you say? The original?
Divided by the updated.
Okay.
So we can just tell by looking. Just look at it. You can tell that the lower two pipes, the f value is not changing a lot there. But on this pipe AD, the f value is still changing a lot. So this isn't exactly the h sub d values. It's going to be slightly different than that potentially. So at this point it's easy for us to copy and paste, so we'll do that. Copy everything, including these percentages. Control C, paste it down into iteration 4, Control V, and so now, what's going to be different in this round of iterations? Well, the F values are different. So here was the beginning F values in iteration 3. The beginning F values in iteration 4 are slightly improved. And so if we run that solver again, or goal seek, then we want the difference to be equal to 0 by changing the guess value of head. It's done. Oh, it was, see, it thinks it's done because that's so close. Now I have to make my point, install solver. Add-ins, solver add-in. All right, so now data, what if analysis, solver. Okay, so I want this to be equal to 0 by changing this. And here in the options, here's where you can tell it how precise it has to be. I'm worried it won't converge if I leave it that precise, and so I'll knock out a little bit less precision. Well, maybe one more. All right, okay. Now solve. Oh, it was close enough, it still solves. So, but let's look and see if the F values have changed much. Let's look at the percentage change of the F values. So we're under 1% for all of them. So these are our accurate F values. These are our accurate flow rates. What we wanted to know was if the F values are converged, if the flow rates are accurate. And now to calculate the pressure, we're going to have to use those flow rates. So before we move on to the pressure, are there any questions on how do we know we're done? We're done because flow in equals flow out, and the F values have settled down to where they're not changing much. All right, last part. We're going to be part 2 here. Find the pressure at junction D. So the head at D, our final guess was that this is how much head there is at D. 109.88. Okay, the elevation of D, its physical elevation, is given as 85 feet. So let's type that in. 85 feet is its physical elevation above sea level or whatever. And now we need to know the velocity head in each of the pipes, because what we'll do is calculate the average velocity head to estimate what is the velocity head at the junction. So velocity head is v squared divided by 2g. So v of pipe AD, v squared divided by 2g. And we can just drag that down for all 3 of the pipes, and then calculate the average velocity head of those 3 pipes. So the average velocity head is 1.11 feet. Because we're going to subtract that out of how much pressure there is at the junction. Here's the definition of head. If we rearrange it to solve for the pressure at D, we know how much head is at D. We know the physical elevation, and we know the average velocity head at D. There's 3 different pipes going in there. That's why we took the average. And we'll multiply it by the unit weight of water. Okay, so the pressure at D is the head at D minus the elevation of D minus the velocity head at D, and then multiplied by the unit weight of water. Anybody know in traditional units, pounds per cubic foot? Good, that's right. 62.4 pounds of force per cubic foot of volume. So there's about 1,400 pounds per square foot, and so how do we change that to pounds per square inch? Divide by 144. Good. 144. So it's 10.3 psi at that junction. That's the water pressure at that junction. So that's unlikely to burst any welding connection at that pressure. All right, well, just in the nick of time. I think I owe you 1 minute from last time, right? So you're getting more than that. I'll post the example that we've just gone through. I'll post a recording of that online, as well as the lecture for Tuesday.